Right. So in the previous lecture, we went through the first 4 steps of process creation, and that is choosing the reaction, and then we choose which recycles and where they go. And number 3 was looking at the separation. That's where we chose 12 atmospheres to separate the HCl and 5 atmospheres to separate the dichloroethane from the vinyl chloride monomer. That was step 3. And then step 4, we had to choose how we change pressures and temperatures. And we said we were going to have a pump. This is the first time I noticed that I've still got elimineer verskille in TP and phase. Half of it Afrikaans. I don't know how that got there. I looked at the PDF that I've uploaded, and that seems correct. Anyway, so in step 4, we were eliminating differences in temperature, pressure, and phase. And here we have a pressure change first, because we know we got to land up as vapor going into the pyrolysis step, because at 500 degrees C, virtually everything is going to be vapor. So the first thing you do if you know you're going to make vapor is to change the pressure. And then after that, you'll have to change the temperature until you get to the bubble point. Then you'll change the phase to vapor, and then after that you have to heat up the vapor further. So this is what this whole TP and phase thing is. You've got to put the phase change as a separate thing, and the reason for that is something we're going to come to, and that is that you can have temperature crossovers if you don't have straight lines. During this temperature change, there's a straight line which is dependent on the CP. So the temperature rises in a straight line according to the enthalpy. And similarly over there, it rises in a straight line according to the enthalpy. Here, the enthalpy can change, and the temperature doesn't change if it's a pure material. If it's a binary material, the temperature changes a little bit. Yeah, Philip, please talk.
So we can't see your pointer.
Yes, yeah, I must keep an eye on. Nobody said it in comments, all right, but I wasn't keeping an eye on the comments anyway. Yeah, please just remind me. Thank you, Philip. Right, so because this temperature change, as we change the enthalpy, the slope of the line with temperature, enthalpy temperature graph, there's a kink in the line as you change the phase, and that's the reason that we have to put these in separate blocks. Anyway, so that was the first 4 steps, and then the 5th step is integrate tasks. And integrate tasks is this thing of actually writing things as pieces of equipment for the first time. So previously we had blocks, rectangular blocks that said change the temperature from 25 degrees to the bubble point of the mixture. Now we're going to say we're going to first put it into a kettle reboiler, and in the kettle reboiler we are going to heat to the bubble point and to the vapor at the bubble point. So we're going to increase the temperature up to its bubble point. As it enters, it'll immediately change up to its bubble point. It will evaporate, and we will only take off vapor at its boiling point, at its boiling points, and only after that will we preheat it. So this is where we decide what tasks we're going to integrate. Here we integrated heating up this liquid, which was at 90 degrees, and we had to heat it up to the bubble point at 242. And we were combining tasks because it heated up from 90 to 242, and we changed the phase in this kettle reboiler. And here we've got the reactor, a piece of equipment. So that's how you would draw a furnace because there'll be a flame in the middle here. These are the tubes that might be going around concentrically around the edge. It might be vertical tubes, but there'll be a flame in the middle, and that will use radiative heating of these tubes because the tubes are at quite a high temperature. Now we are integrating tasks because we are both preheating in a preheater, which is not going to rely on radiative heating. We just cool down the combustion gases that are going out over here, and then as it reaches 500 degrees C, the reaction proceeds, and the reaction is also occurring. So we've combined 2 tasks in this unit operation and 2 tasks in that unit operation. Going backwards, the pump had to come first. It was a liquid, so therefore we give the process flow diagram icon of a pump. We call it a pump, not a compressor, because it is pumping liquid. And going back, this reactor is an exothermic reaction. We are putting in 2 gases, chlorine and ethylene. They are byproducts that tend to be solid, so they can be drawn off at the bottom. And because it's exothermic, we will boil off the lightest component. Now remember, these 2 gases, chlorine and ethylene, react virtually completely. The reaction goes almost to completion. So there's no chlorine or ethylene coming off here, but what boils off due to the exothermic reaction is the product of this reactor, and that is dichloroethane, and that comes off as a vapor because it boils off, and we condense it and we return it to the reactor, and that is the heat removal mechanism for this reactor. Because this is a bubble column, it is well mixed, and therefore if you put in cooler liquid, or you've condensed the liquid, that just converts the vapor into a liquid and keeps the reactor cool at whatever temperature. I don't know why we've got a 90 degrees C and a 50 degrees C. I think the 90 degrees C, you can see a different font, was added later because in the text we talked about this is a 90 degrees C reaction. Dichloroethane boils at, no, that's 146 at 4.8 atmosphere, so I'm not sure at 1 atmosphere. We did have the information, but I think it boils at higher than, or at around 90 degrees C. Okay, right, so this is the sort of thing, going from step 4 to step 5. Step 5, now you've got to consider what equipment you're going to use, rather than just knowing what changes you're going to make. So this is a reactor. The changes we got to make was going from chlorine and ethylene to dichloroethane. Now we've got to consider how we're going to do that, what equipment, and whether we're going to integrate tasks and that sort of thing. Yeah, we've got to choose a pump. Then we've got to choose the equipment, kettle reboiler, choose this as being a furnace, and then normally you would have your product coming off here, which you could condense, but instead of condensing, at high temperatures such as these, you get carbon formation, you get a little bit of char formation. And if you put in a condenser, a standard shell and tube condenser over here, you would risk clogging it or fouling that condenser, fouling the heat exchanger very quickly because of the carbon. So what we'd rather do is to put it through a cooler, a separate cooler, the liquid. We cool the liquid with cooling water in a separate cooler, and we can put in a filter to filter out the carbon, for instance. And that gets sprayed at the top of this tank. So you've got the vapors coming in at 500 degrees C. There's a liquid level control at the bottom here, and you're spraying cold liquid from the top. Hot gases are going through the cold liquid spray and cooling down and condensing, and only vapor at the dew point coming off at the top of that column, because essentially it'll be vapor at the dew point, and this is liquid at its bubble, at the same bubble point that's being recirculated over there. Right, so there we've got vapor coming in, and now we want to go into the distillation column. And what did you learn about distillation columns and quality of the feed? Quality of the feed should be 1, which is liquid at its bubble point. So that's what we're going to try and do first. We're going to cool it. We're going to condense that vapor until we get it into its bubble point. And we need to get it to its bubble point, we actually have to use a refrigerant, because this is a mixture. This vapor line is a mixture of HCl and dichloroethane and vinyl chloride monomer. So you can't use cooling water, you need refrigerant. So there's the heat exchanger there, and that gets to the bubble point, or it'll cool it to a little bit less than the bubble point, so that when you throttle it from 26 atmospheres, this is a 26 atmospheres, 25 there, you throttle it down to 12 atmospheres, and that is your distillation column that separates hydrogen chloride. Right, let's have a look at this question. Does the test every week mean we're writing a test on Friday? No, Fridays is going to be DW Sim. That's just a TUT session, but we'll use one of the 2 lectures for a test. Is an exothermic reactor indicated differently than an endothermic reactor? It's not indicated differently, but it's an exothermic reactor. Every reactor is going to look different, but it usually doesn't matter whether it's exothermic or endothermic. You might have direct heat exchange or indirect heat exchange inside the reactor. You might have heat exchanger inside the reactor. In this case, we're choosing to put one outside the reactor, and that's the sort of thing you need to choose. If it were an endothermic reactor, you might have a reboiler here that puts in vapor to keep the thing hot. So it would look different. But whether you've got an exothermic reactor or an endothermic reactor, let's say you've got coils on the inside to remove heat or add heat. It doesn't really matter whether it's an exothermic reactor or endothermic reactor. It would still look the same. Certainly a furnace would only be the endothermic reactor, because we're trying to add heat at a high temperature. Would we get impurities from the spray quench tank due to evaporation? No. The carbon, the char, is going to be in the vapor. Let's say it's in the vapor phase, but as it cools down, it will be in the liquid droplets. It will go into the liquid droplets, and so this will be a slurry of carbon. You won't get carbon particles going up into the vapor, because it's not a vapor. The char particles. So that's the only impurity that we're going to get here, is the char. And so essentially, this is the 3 components: hydrochloric acid. No, not hydrochloric acid, hydrogen chloride, vinyl chloride monomer, and dichloroethane are the 3 components that will come off over here. So that's why we talk about the dew point, not the condensation or bubble point, because it's a mixture. PFDs from right. Yeah, Angela.
Prof, is the reason why we feeding a vapor into the pyrolysis furnace instead of a liquid just because we don't want it to boil in the pyrolysis furnace?
Yeah, you'll be doing when you design this quench, you'll be doing your energy balance for that thing. And then you'll see that the amount of energy that's in this gas, let's say you've got rid of all of the radiative energy by the time you get up here, and this is just a short piece of pipe up here. It would actually be a proper heat exchanger there. There's not enough heat in this gas. Gas cools down very quickly. It doesn't. You'll find if you've got a gas. This is something I also only realized in practice, that if you've got a pipe with gas in it, the gas cools down extremely quickly. So a pipe that is a 25 millimeter pipe, I always call it a 1-inch pipe. If it's carrying liquid, that liquid will be going at about 2 meters per second, and this is to do with heuristics. You know, if you've got a liquid pipe, it'll be 2 meters per second. If it's a gas pipe, it's going to be 20 meters per second. But the CP of this liquid going through this pipe at 2 meters per second is much higher than the amount of energy contained in the gas going at 20 meters per second. So a gas pipe cools down very easily. So this gas that's where you're combusting to produce hot gas, this hot gas cools down very quickly, and there isn't much energy in that hot gas to actually do the evaporation. So that will fall out in your energy balance, but it will also be something that you can get from heuristics, and that's the next step. That's the next section we'll be doing for a number of weeks. We'll be doing heuristics. And by the way, while we're doing the heuristics, we are unlikely to have lots of tests. I'd like to get through the heuristics before I can ask you a meaningful test. So so that test on the 22nd would actually be a good time to have so you can call it a semester test if you like, but I still like to call it continuous assessment. It might count more. It might count more than the standard once a week tests that we'll be having. So yes, for the next 2 weeks, don't expect any tests. Right. So yeah, so we're going to be doing now. You can see in doing this 5th step, you needed to take a lot of decisions that you had no idea how would you choose to actually use a condenser here to remove the heat, and how would you choose this to be a kettle reboiler. Why would you choose to pump a liquid rather than compress a gas? Why do you use it? There's so many decisions that we've made as we go from step 4 to step 5 and integrate tasks. How do you know, as an inexperienced chemical engineer, how do you know how to make those decisions? And that's pretty much why we are going to be doing heuristics. Heuristics are going to help you identify a certain situation. Let's say that you've got vapor and you wanted to put it into a distillation column. You've learned in CMO that you would prefer that it's better to put in a liquid at its bubble point into a distillation column rather than putting a gas in, to have quality of 1 rather than quality of 0. So that's a heuristic that you've learned over the time. So we'll be doing many different heuristics that will help you complete step 5. Okay, so no, we're not at the end, but that is the last step, and this represents a process. So let's go on to the next slide. What we've done is we did the reaction path. That very first step, 5 steps: reaction path, distribution, separations, temperature, pressure, phase changes, and task integration, getting the process flow diagram together. Those are the 5 steps. And what we did is we had 5 different possible reactions that we could use, and we eliminated some of them, and we decided, well, let 3 looks the most promising. That was based on the gross profit margin, and then we went on to doing the distribution of chemicals. How are we going to do the recycles? And we decided to recycle the dichloroethane only back to the pyrolysis reactor and not back to the first reactor. So, those were the 2 options that we had. So there might have been several options, and we've chosen the one where we recycle to the beginning of the pyrolysis reactor. So that's the choice we made. Then separations, we could choose. Now, what are we going to separate first? We chose to separate hydrogen chloride because it is toxic and it requires special materials of construction, and so that would be an expensive thing, and therefore you would want to separate it out as quickly as possible. And that's the choice that we made. There may have been other choices. We could have, for instance, taken out the least volatile component first. That would have been the dichloroethane, but we've chosen, because we wanted to get rid of the toxic material as quickly as possible out of our process, which took the HCl out first. Temperature, pressure, and phase changes. There were many decisions that we had to make there, and out of the decisions, we eventually landed up at task integration, and again, we had to take many decisions in task integration. So you could see this is a tree, and there would have been many different designs that could have come out, that you could have landed up with in how to make this material, vinyl chloride monomer. Now, this is really the crux of design. This is how I can best explain design. Design is not getting something that would work. It would be possible to go this route of using acetylene to make vinyl chloride monomer, and we would have gone through a whole tree of decisions using acetylene as our raw material, and we would have had a design that worked. It might have blown up, but it might have worked for a few weeks. And that doesn't mean that it's the best design. So when you do design project CPJ next semester, the aim of CPJ is to come out of all of these designs that you can come out at the end. The essence of design is coming out with the best one that's possible, not one that works. One that works is easy. You've spent 3 years doing the calculations that you can say, yes, if I have this many plates in my distillation column and this much reflux ratio, it will work. But that doesn't mean it's the best design. And this little table, this little tree, as we call it, represents the design process. We want to find the best thing that's possible over here. Okay. So algorithmic methods are very effective for the synthesis, analysis, and optimization. And those will be covered in section B, which is really algorithmic methods are more like designing heat exchange networks. It is the thing where you can use equations to actually calculate stuff. You can see that in these previous decisions we've taken to arrive at this thing, there was no equations as such. There was this equation that we might have had to do about the enthalpy change. If we had to change the enthalpy from liquid to vapor at 500 degrees C, maybe there wasn't enough enthalpy in the gas. So that would be an algorithmic method. But most of these things are simply design decisions, and they are typically based on heuristics, and that's what we're going to do in the next section. So, so algorithmic methods are these methods that you've been practicing 3 years to do. But now we're looking at real design, and that design doesn't come from calculations as such. It comes from really common sense. You could call it common sense, but this common sense needs a certain amount of knowledge, and that knowledge we're trying to impart using heuristics. Right, so now, finally, this is a process flow diagram. Okay, so note it's different from that previous step 5. The process flow diagram shows pieces of equipment. So this bubble column you show as a tank, that heat exchanger you show as a heat exchanger, with that sort of, we designate the cooling water that goes through it. We label streams, usually with a triangle. There's another heat exchanger, high pressure steam heat exchanger, a pump P, represented as a P100, and P100, well, it's described over here. If we look at R100, it's described close by. I'm not so keen on this sort of notation. I actually prefer the pyrolysis furnace being written close by to this thing. But it's up to you. Every company has a different standard, but there are some standards about writing process flow diagrams. And the icons that you use are pretty standard. So here is a furnace, and it looks like a furnace. Yes, this is a PFD, a process flow diagram, and not a P and ID. A P and ID would have the instrumentation and the control. It would show how these temperatures are controlled. At one stage, we had this V100 quench tank has got a level control in it, and we're not even showing how that level control works. We're just saying we are pumping liquid through there, cooling it down, cooling water, and pumping it back into the top. So not that much detail of the equipment, but it does show that is a quench tank, that is a pyrolysis furnace, a distillation column, a elongated tank with dotted lines that will show the trays in the distillation column. Heat exchangers showing medium pressure steam, high pressure steam. Where was the high pressure steam? There's cooling water. This one would have FB. That's the refrigerant, RB, I think that is, not FB. PR. That also needs refrigerant. I don't know that. I don't know the R and the P for refrigerant, but the R stands for refrigerant. That was a refrigerant to get the HCl cold enough. And there we have HCl. What else do we need to show? Yes, Philip?
So what happens between stream 9 and 10? Because I only see a valve there, and I don't really understand why
that is,
you would.
Yeah, that's a change of pressure. And this is also something that I like to see in process flow diagrams, because as a chemical engineer, you want to be able to go through this thing and understand what's happening, what processes are happening. So why would you put this valve here? We had to go from 25 bar pressure at V100 down to 12.6 bar or something like that to separate out the HCl. And so that is the pressure relief. That's a pressure reducer. And we're going to do a heuristic that says whether we use a pressure relief valve there or whether we put in a turbine there. In other words, we recover the energy going from the high pressure to the low pressure, and we generate electricity or generate power from there. And it only pays to put in a turbine there when we've got a high a certain amount of power. I think it's 15 kilowatts or 15 kilowatts for vapor and 150 kilowatts for liquid, something like that. Just something useful. What are the squares with numbers? Looking for a square with numbers.
I think he refers to the streams, the diamonds.
Oh, the diamonds, right. Yeah. So that's just a stream. It's a stream name. It might be S-13. It might be S13. It might be, even in Aspen or DWSim, you can call that stream whatever you like, which is more descriptive. But with big flow sheets, it's better to have numbers so that you can quickly look them up from what we call a stream table. Yeah, but it's important to designate them so that we can refer to a certain stream. You need to be able to refer to this stream. When Philip asked his question, why is there a valve on stream 9? It's good to be able to refer to a certain stream. Right, and yes, that's it. Process flow diagram. I've given you. You've got a number of different symbols that we are using in this one. What I'm looking for from you in the exam is that you use this sort of notation, this sort of arrow pointing to the right for stuff coming into the flow sheet, and that same sort of arrow again pointing to the right for stuff going out of the process, out of the flow sheet. So it's, again, this represents an arrow. You shouldn't have the arrow pointing this way. It shouldn't, it should be. Generally, we have the notation that we like to go from left to right. But these represent arrows. And that's where you write what is in that stream. So that is one thing. I will give a mark when you have to do in your exams. You've got to write a process flow sheet as step number 5. I give marks for that. I give marks for showing your condenser and reboiler on your distillation columns. You can't just put in a distillation column and say the stuff that comes out the top is that, and the stuff that comes out the bottom. You've got to have that equipment shown. What else do I give marks for? I give marks for having a pump on the recycle. This stuff is not going to just automatically flow to the start of that pump. Well, I suppose that it's possible because that is a pump. So actually, I don't really see the need for that pump. Anyway, I give a mark for showing that you've got the recycle stream in place, that you've got a pump before you do the evaporation, the boiling of the liquid. I will give a mark to show a furnace as a furnace. So essentially, it's not so much about your process flow diagram itself, the flow of, what a process flow diagram is about. I'm just looking for you to showing the notation correctly when you draw a process flow diagram. No pumps or compressors for utility streams. And yeah, that's right, Luca. It is possible to put this, well, firstly, the reason that I thought this is not necessary is that this is operating at atmospheric pressure, this R100. So this T over here is at atmospheric pressure, and this distillation column was operating at 4.8 atmospheres. So essentially, you can have a valve, a control valve, rather than a pump over there to go back to recycling this. Oh, right, cooling water. This is at its bubble point. Again, very strange to put the pump where you will get that. You will get, if something's at its bubble point, the inlet to the pump. What's it called? Come on, somebody. yeah, you'll get cavitation because of the
Suction,
net
right?
positive suction, net positive suction head or something like that. Yeah. So that looks like a really funny place to put a pump. You would rather cool it down first and then put the pump, or as I would say, not have a pump at all here. Cool it down, and then you would have a throttle valve, control valve, to control the flow into the recycle. Right, so those are the sort of things that I'm looking for when you do these things, and that if you've got a distillation column, that you've shown the distillation column icon correctly and things like that. You've got that you've got heat exchangers drawn as heat exchangers. All of these heat exchangers that you see here are actually drawn as utility heat exchangers, and then in CPS 420 next semester, we will learn how to integrate heat exchange. So that is typically something that you would use the heat of this stuff coming out of your furnace to exchange with the stuff going into your furnace. So you can recover the heat going out of a reactor to heat up stuff going into the reactor. And even those, it is more convenient to represent them as heat exchangers in this way. So you would put a heat exchanger. Okay, in this case we've got a more complicated heat exchanger arrangement. But if we put a heat exchanger there, we would refer to stream 5 as the utility, and over here we would refer to stream 7 as the utility going through that one, rather than trying. Otherwise, you get really complex streams going through your process flow diagram. It may be that you need to exchange this stream with stream number 5, and if you try and put in a line that shows how these two, that the one process stream and he's heating up the other process stream, it gets really complicated and muddles things rather than makes them clearer. Right. One more slide, and that's just to summarize what we did with process creation. So that is the end of process creation. We had to get data. Data is usually available, for instance, on your DW Sim or Aspen, whatever you're using. Experiments only if necessary to verify crucial data before you go and build a big plant. Preliminary process synthesis, top-down approach, do that synthesis tree of design alternatives so that we can find the best alternative, not just an alternative that works. And it's illustrated by the synthesis of vinyl chloride monomer and the TPA processes. Development of a base case design, focusing on the most promising alternatives from the synthesis tree. And when we talk about a base case design, it is that. That is the base case design, together with its mass flows and energy flows, mass and energy balances, that say how much of every component is in every stream. That is a base case design. And once you've got your base case design, you can go on to much more more detailed design, where you can go and design your reactor. So that pyrolysis furnace, you would need to look at the radiative energy and how many tubes and what the area of the tubes is, and view factors and whatever you need to do to design a radiative furnace, radiative heat exchange furnace. So that is where you go into detailed design. But at this stage, having done the process synthesis and the base case, once you've got your base case, you know what the mass flow is, and you know all of the components' mass flows. You know how much energy you must impart, and you know what the temperature is that you got in your base case design, and the mass flow of stream 7. So you've got everything already. And in your design project, you will be ending up with this base case design after you do the group work. So the group work will be when you do the process synthesis and land up with the base case. And after that, you will go into individual design. Individual design, you will need to do the process control system based on this base case design. You will have to do a reactor design. You will have to do a distillation column design, and you will have to do the safety and environmental considerations for this plant as a whole. Plant layout, things like that. So base case design, getting to this base case design, which we've called process creation, involves is what you will be doing in your group work. You work in groups together to eventually land up with the best alternative in the synthesis tree, and that will determine your mark, your group mark in the design project is your semester mark, and your semester mark depends on how well. Let's just go back one. Which of all of these, and there are actually thousands of different alternatives that you might land up with. So your group lands up at this point, for instance, and your mark depends on how good is that as a solution, as a design, compared to, let's say that this is the best design. How close is it to achieving the safest and most economical process to make that thing? So I thought that I was going to go on to heuristics first few lectures, but I think the last 4 slides has taken us the whole lecture. But it's really important, and for you to understand what process synthesis is about and what we're trying to achieve essentially is get to process flow diagram. That's the base case design. Process creation is about getting a base case design, and heuristics, the next section, is there are lots of decisions you have to make to get to this design and how to make the best decisions. That's heuristics. All right, I'm going to stop the recording and then I'll take questions.